Okay, today we're going to be looking at tutorial 4b, which is a constraint optimization problem. We are considering the function g of x, y, and z, which is equal to x multiplied by y multiplied by z, and the constraint f of x, y, and z, which is equal to b minus x minus a half y minus 3 over 2z, and b is greater than 0. Write down the Lagrangian for the optimization problem, the maximum of the function g of x, subject to the function f of x, which is equal to 0. Okay, the definition of the Lagrangian is we have the function g of x comma y plus lambda f of x comma y. You can use a minus sign here, but it's better to use a plus. So using this, we get our Lagrangian as xyz plus lambda brackets b minus x minus a half y minus 3 over 2z. If we now work out the first order conditions, we will partially differentiate the Lagrangian with respect to x first. We get yz minus lambda, which is equal to 0. If we partially differentiate with respect to y, we get xz minus a half lambda is equal to 0. And if we partially differentiate with respect to z, we get xy minus 3 over 2 lambda is equal to 0. And if we partially differentiate with respect to lambda, we are just left with the constraint, which is equal to 0. Cool. If we now solve these equations, we will find our four solutions. So if I rewrite those first order conditions, we have yz minus lambda is equal to 0, xz minus a half lambda is equal to 0, and xy minus 3 over 2 lambda is equal to 0, and then the budget constraint, b minus x minus a half y minus 3 over 2z is equal to 0. If I begin by making lambda the subject for these three, we get lambda is equal to yz, lambda is equal to 2xz, and lambda is equal to 2 over 3 xy. Now I will begin by equating equation 1 with equation 2. So yz is equal to 2xz. If I divide by z, when I do that, I get rid of a solution, which is z is equal to 0. I get y is equal to 2x. If I equate equation 1 with equation 3, I get yz is equal to 2 over 3 xy. If I divide by y, I get rid of a solution, which is y is equal to 0, and we get z is equal to 2 over 3x. And lastly, if we equate equation 2 into equation 3, we get 2xz is equal to 2xy over 3. Again, move the x's, and noting down x is equal to 0 is the solution that we got rid of. We get 2z is equal to 2y over 3. So z is equal to 1 over 3y. Cool. So now we have a solution where if I keep x the same, so this will be x, y, z are variables, y in terms of x would be equal to 2x, and z in terms of x would be 2 over 3x. So this is a solution. If we sub it into our constraint over here, we get b minus x minus a half 2x minus 3 over 2 over 3x is equal to 0. We get b is equal to minus x minus x minus x is equal to 0. So b is equal to 3x, and therefore x is equal to b over 3. So our solution in terms of b is b over 3, 2b over 3, and then 2b over 9. And if we were to work out the value of lambda, we can use lambda is equal to yz. So if we multiply these two, we get 4b squared all over 27. So we have our first solution, which is 4b squared over 27, b over 3 as x, 2b over 3 as y, and then z is equal to 2 over 9b. If we are going to work out these other solutions, we now need to consider z is equal to 0, y is equal to 0, and x is equal to 0. So if I begin with x is equal to 0 and sub it into y is equal to 2x, then we get, so therefore y would be equal to 0 as well. So we have 0, 0, and then some value of z. If we sum this in to our constraint, which was b minus x minus a half y minus 3 over 2z is equal to 0, we get b minus 3 over 2z is equal to 0, therefore z is equal to 2 over 3b. So our solution is 0, 0, 2 over 3b as z. And if we were to work out lambda, lambda is just y times z, which is going to be 0. Cool. So if we chuck that in, we get lambda is 0, x is 0, y is 0, and then z is 2 over 3b. If we now consider y is equal to 0 and sub it into this equation to find z, so sub into z is equal to 1/3 y, we then get z is equal to 0. So we're left with some value of x and then 0, 0. If we sub this into the constraint, we get b minus x is equal to 0, therefore x is equal to b. So our solutions are b, 0, 0, and our value of lambda is these two multiplied together, which is 0. So lambda was equal to 0, x was equal to b, y was equal to 0, and z was equal to 0. And finally, if we use z is equal to 0 and we sub it into z is equal to 2 over 3x, this leaves us with x is equal to 0. So we get 0, some value of y, and 0. Subbing this into our budget constraint leaves behind b minus a half y is equal to 0. So b is equal to a half y, so y is equal to 2b, and lambda is equal to 0. So we get 0 as lambda, x as 0, y as 2b, and then z as 0. So if I just write that in a neater way, we get b over 3, comma 2b over 3, comma 2b over 9, 0, 0, 2b over 3, b, comma 0, 0, and then 0, comma 2b, comma 0 as our four solutions there. Cool. Moving on. Calculate the bordered Hessian for the general lambda x, y, and z, and determine the projected bordered Hessian in each of the four local optima. Cool. To work out the bordered Hessian, we will first define it. So the bordered Hessian is defined by 0 and then the first derivatives of the constraint, and that follows the same over here. And then we just have our normal Hessian left behind, so the second derivatives of the Lagrangian function. Cool. If I now just remind ourselves of the Lagrangian function and the first derivatives. So the Lagrangian function was a function of variables x, y, z, and lambda, which was equal to x, y, z plus lambda b minus x minus a half y minus 3 over 2z. And our first derivatives of this function were those. So if we start filling this in now, if we look at our constraint and differentiate it partially with respect to x, we get -1. Partially differentiating with respect to y gives us -1/2, and partially differentiating with respect to z gives us -3 over 2. If that now follows on over here, so we get -1, -1/2, -3 over 2. If we now work out the second derivatives of each of these, differentiating this partially with respect to x again gives us 0. Differentiating this partially with respect to y leaves behind z, and partially differentiating this with respect to z gives us y. Partially differentiating this with respect to x gives us z. Partially differentiating this with respect to y again gives us 0. And partially differentiating with respect to z gives us x. And then as our last row, when we partially differentiating this, we get y, x, and then 0. So here's our bordered Hessian. Now, to work out the projected Hessian, we use the formula Hessian, which is projected is equal to the transpose of z multiplied by the Hessian multiplied by z, where z is equal to basis vectors which are orthogonal to the Jacobian, and h is just the Hessian. So just these values, so that would form a 3 by 3 matrix. Okay, if we first work out the Jacobian is just the first order derivatives. It's the first order derivatives of the constraint for our case. So we've only got one constraint, so all we're basically doing is just working out the gradient of our constraint over here. So the first order conditions were -1, -half, and -3/2. So we have -1, -1/2, -3/2. Now we need to find a convenient basis of vectors which are orthogonal or perpendicular to our gradient of f. So one vector that we could have is -1/2, 1, and 0. And that's because when we do that vector dotted with our gradient, we get 0, because we do -1 times by -1/2 plus -1/2 times 1 plus -3/2 times 0, and we get a half minus a half plus 0, which is 0. So when we dot this vector with this, I should say the transpose of that, we get 0, hence they're orthogonal. If we now get another vector, we could have -3/2, 0, and 1. So now, if I form this vector z, we have -1/2, 1, 0. So this vector just takes the form of v1 in this column and then v2 in the next column. Now, if I work out the transpose of z multiplied by h multiplied by z, we have -1/2, 1, 0, and then -3/2, 0, 1. As z transpose, our Hessian was 0, z, y, z, 0, x, and y, x, 0. And then the matrix z is just a half -3/2, 1, 0, 0, 0, 1. Okay, so this is a 3 by 3 matrix, this is a 3 by 2 matrix, and this is a 2 by 3 matrix. If I begin by multiplying these two, I do this row multiplied by this column, which gives us z and y, and -1/2 z, -3/2 z plus x, and -1/2 y plus x, and just -3/2 y. Now, if we multiply these two matrices, we get -1/2 z, -1/2 z. Then we get -1/2 y, -3/2 z plus x. Then we get -3/2 z, -1/2 y plus x. And we have -3/2 y, -3/2 y. If I now simplify this, we get -z, x, -1/2 y, minus 3 over 2z, x minus a half y minus 3 over 2z minus 3y. So here is our projected Hessian. Now, if we sub in our solutions, our first solution was b over 3, 2b over 3, and 2b over 9. Subbing that in to our projected Hessian, we have minus 2b over 9 minus 1/3 b minus 1/3 b minus 2b. If we now look at our second solution, which was 0, 0, 2 over 3b, we get minus 2 over 3b minus b minus b 0. Our third solution was b 0, 0. Using this, we get 0, b, b 0. And our fourth solution was 0, 2b 0, which gives us 0 minus b minus b minus 6b. Okay, so these are our projected Hessians. So now, part D says calculate the characteristic equations for the eigenvalues of the projected Borden Hessians in all 4 local optima and find all local maxima. So now we have to use the characteristic equations. So if I start off with equation 1, we have the determinant of the matrix minus lambda of the identity matrix. So we need to find the determinant of minus 2b over 9 minus lambda minus 1 over 3b minus 1 over 3b minus 2b minus lambda. If we now work out the determinant, so we get this equation, which is y squared plus 2b over 9 plus 2b lambda plus 4b squared over 9 minus 1 over 9b, and that's going to be equal to 0. Cool. If we do this for this matrix over here, we need to find the determinant of this matrix, which will be minus 2 over 3 b minus lambda multiplied by negative lambda minus b multiplied by b. So now we get 2 over 3 lambda b plus lambda squared plus b squared. So we are left behind with y squared plus 2 over 3 b lambda plus b squared is equal to 0 as our characteristic equation. Cool. If we now look at this matrix, we need to find the determinant of this matrix minus lambda b, b minus lambda, which will be lambda squared minus b squared. So our characteristic equation is lambda squared minus b squared. And doing the same thing for our fourth matrix, we get lambda squared plus 6b lambda minus b squared is equal to 0 as our characteristic equation. Cool. So now to work out if those solutions were maximum, minimums, or saddle points, we need to find the eigenvalues, which just means we need to solve these characteristic equations. We can let b is equal to 1 and say y squared plus 2 over 9 plus 2 is 20 over 9 lambda, and then plus 3 over 9, which is 1/3, equal to 0. So we get this. So lambda is minus 10 plus root 73 over 9, or it is minus 10 minus 73 over 9. This is roughly minus 2.06. This is roughly minus 0.16. So as both eigenvalues are less than 0, this is a maximum. So a characteristic equation for solution number 2 is a lot easier, so that we can solve just with b in it using quadratic formula. So we have minus 2 over 3b plus or minus square root b squared minus 4ac all over 2a. When we solve this, we have minus 2 over 3b plus or minus, okay, well, this doesn't look right, so I've made a mistake somewhere. If we go back up, so, right, so I've forgotten this minus b, and that just makes this a minus b, so we get minus b squared over here. So now we just get 4 over 9b squared plus 4b squared, which is 40 over 9b squared all over 2. If we simplify this a bit more, we get minus 1/3 b plus or minus root 10 over 3b. So our two values of lambda would be minus 1/3 plus root 10 over 3, and lambda is equal to b minus 1/3 minus root 10 over 3. So this is going to be negative, and then minus 1 over 3 plus root 10 over 3 is positive, so this would be positive. So as the eigenvalues are different signs, it is a saddle point. This solution is a saddle point. Okay, if we do solution number 3, our characteristic equation was y squared minus b squared is equal to 0, which is nice and easy. We get y squared is equal to b squared, so y is equal to plus or minus b. For that same reason, we get this as a saddle point, as we have different signs for the eigenvalues. And number 4, we had y squared plus 6b lambda minus b squared. If we solve this using quadratic formula, we have minus 6b plus or minus square root 36b squared minus 4ac all over 2. So we get minus 3b plus or minus root 10b. So that gives us minus 3 plus root 10 as one value, and then lambda is equal to b minus 3 minus root 10. So this will be negative, and this is positive. So we get another saddle point. So going up, there's only one equal maximum, which is this one. Cool. Moving on to 16. Jacobians. Consider the utility function y of x comma y is equal to x multiplied by y, and the matrix A, which is 0, 1, minus 1, 0, calculate the gradient of this utility function and the vector field, which is the gradient of this utility function multiplied by the matrix A, and show that these vector fields are locally orthogonal everywhere. Okay, cool. So to work out the gradient of this utility function, we have to take partial derivatives with respect to x and y. So we get, when we differentiate this with respect to x, we get y, and when we differentiate it partially with respect to y, we get x. So the gradient is y comma x. And then to work out the vector field B, we have to multiply u, which is y comma x, by the matrix A, which is 0, 1, minus 1, 0. When we do that, we get minus x and y. So here we get minus x comma y. Now we need to show that they're orthogonal. To do that, we need to show that the dot product between these two vectors is 0. So yx dotted with minus xy will give us minus xy plus xy, which is equal to 0. So as u dotted with b is equal to 0, they are orthogonal. Next question, consider the function r of xy, which is equal to minus x squared over 2 plus y squared over 2, and the coordinate transformation xy maps to yr. Show that the vector b, which is equal to the gradient function of r of xy, and calculate the Jacobian of the coordinate transformation b. Okay, so in order to do this, we need to work out the gradient of this function r, which is a function of x and y. To do that, just like before, we're going to take partial derivatives with respect to x and y. So that gives us minus 2x over 2, and then 2y, over 2. And this is equal to minus x over y, and minus x comma y was b. And it's shown. And calculate the Jacobian of the coordinate transformation b. So the Jacobian is just the first derivatives of our function u and of our function r. So we have the partial derivative of u with respect to x and with respect to y, and the partial derivative of r with respect to x and with respect to y. So this bottom row we can fill out, it's just this minus x and then y, because that's what we did here. And then the top row is simply just over here, so yx. Cool. Find the inverse transformation, so b minus 1, so this time u and r map to x and y, by determining the functions x, which is a function of u and r, and y, which is a function of u and r. Okay, so right now we have the functions r is equal to minus x squared over 2 plus y squared, and we also have the function u is equal to xy. And we want to make x a function of u and r, and then y a function of u and r. So in order to do this, this should be y squared over 2. I'm first going to rearrange this function so that we have 2r is equal to y squared minus x squared, and rearrange this function so we have u over y is equal to x. I am then going to substitute this into here, so we get y squared minus u squared over y squared. If I now multiplied by y squared throughout, we get 2ry squared is equal to y to the power of 4 minus u squared. Bringing everything to one side, we have y to the power of 4 minus 2ry squared minus u squared. If I now, so this is a disguised quadratic, so if I now use quadratic formula, I have y squared is equal to 2r plus or minus square root 4r squared plus 4u squared all over 2. Here we have x and y are greater than 0, so we can ignore the negative solution. So we will get y squared is equal to 2r plus, if I take the root 4 out, we get 2 square root r squared plus u squared all over 2. And this will be r plus r squared over u squared. So therefore, y as a function of u and r would be square root r plus root r squared plus u squared. And to find out x, we simply sub it into here. So x is equal to u over square root r plus root r squared plus u squared. So u over r plus square root r squared over u squared. Now, part D. Consider the constrained optimization problem where we have to maximize the function u subject to the constraint x plus py is equal to b. Write this as an optimization problem in the coordinates u, r. Determine what the Lagrangian and the first order conditions would look like, and can you solve it? Okay, so the Lagrangian would be our function u, which is a function of x and y, plus lambda b minus x minus py. Now, this is the same as writing xy plus lambda b minus x minus py. But they want to write this optimization problem in the coordinates of u and r. So xy multiplied is just u, and then plus lambda b minus x is this over here, which I will write as x as a function of u comma r to save time, and minus py as a function of u comma r. So this is what our optimization problem would look in the coordinates of u and r. So that's the Lagrangian. And the first order conditions, if we partially differentiate the Lagrangian with respect to u, we just get 1 plus lambda minus the partial derivative of the function x with respect to u minus p and the partial derivative of y with respect to u. So this we can write as 1 minus lambda. Cool. So that's one of our first order conditions. If we equate it to 1, we will get 1 is equal to lambda partial derivative of x with respect to y plus p partial derivative of y with respect to u. If we now differentiate the Lagrangian with respect to r, we get lambda minus the partial derivative of x with respect to r minus p, the partial derivative of the function y with respect to r. So equating this to 0, we get minus lambda. We get this. And if we partially differentiate the Lagrangian with respect to lambda, we just get the budget constraint, or the constraint, which is b minus x u comma r minus py and ur. So that's a constraint. So this is what the first order conditions would look like. Can you solve it? So solving these first order conditions will be a bit tedious. So if we go back to this Lagrangian, so in the coordinates x and y, so we have the Lagrangian which is equal to xy minus lambda b minus x minus py. It's a lot easier when we work out the first order conditions. So we get x minus p lambda over here, and then when we differentiate with respect to lambda, we get the constraint. So rearranging this, we get lambda is equal to y. Rearranging this, we get lambda is equal to x over p. Equating these together, we get y is equal to x over p. If we now plug this into the constraint, we get b minus x minus p x over p. So the p's cancel. So we get b is equal to 2x. So x is equal to b over 2. To work out y, using this, we have b over 2 divided by p, which is just b over 2p, and then lambda is the same as y, so lambda is b over 2p. To now change this to our UR coordinate system, u was equal to x multiplied by y, so x multiplied by y, which is equal to b squared over 4p, and then r was minus x squared over 2 plus y squared over 2. So that would give us minus b squared over 8 plus b squared over 8p squared. And this can be written as b squared over 8, 1 minus p squared minus 1. And then lambda will stay the same. Lambda is still b over 2p. Cool. So that was the end of this tutorial.